Hi, I'm Christophe de Vos, working at the RSC Group in Belgium for RSC Technologies, and I will present today some new robust approaches and techniques to encounter analytical drawbacks and improve current analytical methods in GC. My talk will be mainly related to GC sample introduction and injection techniques, pointing out some recent developments related to the analysis of volatiles, but also to the current methodology we use to improve sensitivity when doing liquid injection. And this more specifically applying large volume injection within routine analytical methods. Let's have a start with the analysis of very volatile and volatile compounds in GC. And when going through these first slides, we try to focus on their analysis in water samples. However, the presented approaches and techniques can be expanded more widely towards other applications, type of samples and specific markets. And as the topic of today is troubleshooting in GC, what is better than presenting on sample injection? Always been the Achilles heel in GC. Important to note here is that a good injection is an injection without alteration of the sample and without contribution to band broadening. For instance, the headspace injection of volatiles often suffers with an important contribution to band broadening because of a slow injection and the fact that volatiles do not have a lot of retention. Therefore, often we obtain lack of sensitivity and showing ugly distorted peaks in the chromatograms. And this to mention that standard headspace injection is already performed in split mode, giving the general static headspace injection technique the label of having low performance in terms of sensitivity. GC analysis in general covers a number of compounds, around 60 in the range of dichlorodifluoromethane to the 3-chlorobenzenes, which are listed in several norms and governmental procedures. Over the last decade, quite some new volatile compounds, also very volatile compounds, were added to the analytical expectations in different markets. And here, depending on the industry and type of water sample, some additional compounds, very diverse in their chemical properties, such as epichlorohydrin, volatile thiols like methylmercaptan, or for example haloacetonitriles also need to be analyzed. Let me show very fast what conventional static headspace does. As the technique is quite simple, we must note the high robustness of the technique. However, as mentioned, injecting in split 1 to 5 to 1 to 10 and then taking a volume of 500 microliters to 1 ml from the vapor phase, at the end results in limited sensitivity. To start, the sample is incubated at high temperature, around 80 degrees, before a part of the headspace is taken by a headspace syringe or filled within a loop and then injected. When applying standard headspace injection to determine vinyl chloride, a very volatile compound eluting here at 3.9 minutes on a typical VOC column, we clearly encounter band broadening resulting in a distorted peak. This analysis, often done in a routine using a standard MS single quad source, even with a split injection and so a faster transfer towards the column, still shows at the 500 ppt level, but even so at the 5000 ppt or 5 ppb level, the contribution of the injection to band broadening. Calibration can be perfectly done in the 500 ppt to 50 ppb range, using a proper internal standard, but ion ratios, especially in the low range, can sometimes be out of spec. The same analytical method applied for trichloroethylene, for example, shows better performance. Of course, still showing the limited sensitivity obtained by conventional static headspace injection, nevertheless sometimes sufficient for the area we work in. This can be clearly observed from a 500 ppt and 5 ppb level spiked water sample, depicted here. But again, calibration within a sometimes acceptable range shows a good result. But let's have a look now of what last year has changed in the routine analysis of volatiles. Besides the number of compounds that have to be analyzed at once, in routine also the requested limits decreased, where several industries now have to go down to the low ppt level for a long list of volatile compounds, with often high diversity in chemical properties. Here an additional cold trap to refocus the volatiles at the beginning of the column has become the standard even in routine, without bringing harm to the robustness of the static headspace technique. Adding a refocusing trap to the static headspace standard setup only means a modification within the oven. Installing the cold trap and the proper way to focus the volatiles at the beginning of the column. Installing, for example, an empty pre-column through the cold trap and in front of the analytical column. Of course, we need additional cooling assistance to be able to lower down the temperature of the cold trap. This with most flexibility using liquid nitrogen, but having also some other alternatives ready, depending on the lab and depending on which type of volatiles need to be analyzed. Please take note of the remark added at the bottom of the slide, where of course the overall sensitivity of our headspace method will also depend on the choice of mass spec, equipped with a certain type of source. Main advantages of having the refocusing of the volatiles is the ability to inject in splitless mode, immediately increasing the sensitivity of the method with a factor 10. Besides this, we eliminate the contribution to band broadening of the headspace injection, especially for the very volatile compounds eluting fast. Again here, at the same time, because of the sharper peak shape obtained, sensitivity increases also. What happens now regarding the GC parameters to be optimized to get a proper injection and headspace analysis using on-column refocusing? First, as splitless injection is performed and the volume injected is kept standard, 1 ml, the transfer towards the column is even slower now. So the speed of injection is programmed this way, taking into account the column flow during injection. Instead of injecting at 300 microliter per second, we now lower to 25 microliter per second. This way, not generating an overpressure in the injector. Transfer is rather slow, still using of course the standard narrow 2 mm headspace liner in the injector, but the volatiles are refocused at a cold trap, based on the cooling temperature, number of coils through the cold trap, and in some cases the combination with the stationary phase present in the capillary, situated in the cold trap. All parameters of the cold trap must be controlled and programmed in the software, with high importance towards the speed of heating the device, which in fact is the real injection towards the analytical column. Let's now compare results for the same compounds analyzed and already presented. Here, vinyl chloride trapped at -120 degrees with liquid nitrogen shows a perfect peak shape at the 500 ppt level, but also at the 50 ppt level, illustrated at the top right. No distortion is observed. Splitless injection results in a 10 times gain in sensitivity, making it possible to calibrate in a wider range and lower down the limits that we can achieve with standard mass spec detection. The same for trichloroethylene, a 10 times gain in sensitivity, and peak shapes are maintained perfectly. An ideal approach to do general VOC screening of the target list requested. And as said, keeping the robustness of the static headspace technique throughout the required validation experiments. The choice of mass spec and the influence on sensitivity linked to the source selected is shown here using the most sensitive Hess source. Vinyl chloride and chlorobenzene shown at the 500 ppt level, but calibrated from 10 ppt to 1 ppb. Limits obtained never possible before using conventional static headspace injection. Now a complete VOC solution can be tailored depending on the requirements needed for the specific lab. To summarize, as splitless injection is done, an immediate 5 to 10 times gain in sensitivity is achieved. Here shown for the second half part of a typical VOC chromatogram from toluene to the trichlorobenzenes, eluting at the end of a typical VOC stationary phase, VRX or 624 analytical column. Important, we eliminated the contribution of the headspace injection for the very volatile compounds, traditionally a drawback of the static headspace injection technique. You see the first part of the VOC chromatogram now, up to a retention time of 9 minutes, where besides vinyl chloride, also other very volatiles like chloromethane and dichlorodifluoromethane have perfect peak shapes, astonishing with even better base peak width than the typical 0.1 minutes or 6 seconds normally obtained on a narrow bore capillary column, a little more than 3 seconds. A small calculation here is made for a water sample at the 10 ppt level. When assuming full headspace presence of the volatiles and taking standard conditions for headspace with on-column refocusing, so 1 ml injected in splitless mode, we arrive in the sensitivity range where state-of-the-art mass specs easily detect these absolute quantities. Low ppt level with static headspace has become standard. And again, when needed to boost your sensitivity, modifying the sample amount taken and the volume injected, the same calculations for 10 ppt using a 2.5 ml splitless headspace injection is made. We must say that now we even can go down to ppq level in VOC measurement in combination with the sensitive mass spec. The trace of water was measured simultaneously, in red at the bottom of this slide, showing of course a huge amount of water vapor brought onto the column, however almost not interfering with the VOC analysis as such. This summarizes the different headspace techniques we have in our toolbox. No need to discuss all in detail here, but just note with this slide the possibilities of injecting multiple times a headspace amount of the same sample and trapping the volatiles, generating one single chromatogram for these multiple injections. Secondly, we will move further to dynamic headspace enrichment, boosting the sensitivity again and see what on-column focusing can contribute here. Finally, I will illustrate that even a more selective enrichment technique, like headspace SPME, can show high analytical performance for some typical applications and type of compounds when combined with on-column refocusing using the CTS2 cold trap. To overcome the difficulties we encounter with more hydrophilic volatile compounds, as they bring more selectivity to the static headspace enrichment and resulting in low sensitivity using a default sample amount, 5 to 15 ml of water sample in the vial, we can move to a full evaporation headspace technique starting from only 10 to 100 microliters of sample in the vial and evaporating the total amount completely at 80 degrees. The result of this is depicted in both chromatograms where a same amount of a mixture of volatiles is spiked but where full evaporated static headspace only takes a small sample volume. Here, from the lower chromatogram, clearly you see the non-selective detection of all VOCs, also the more hydrophilic compounds, suffering from low sensitivity when applying the standard headspace approach shown on top. Another approach is feasible for these more hydrophilic compounds, applying the multiple injection of the headspace in combination with on-column refocusing. When targeting these type of compounds, we could increase the volume injected, here for example 2.5 ml, half of the headspace volume, and inject multiple times this amount. All is trapped at the beginning of the column, and one single analysis is performed. During these studies, the idea is always kept that additional stationary phase at the cold trap will influence the trapping performance, and so in parallel, some microtrap capillaries were tested with different phases, while at the same time cooling alternatives were investigated. This to avoid the use of liquid nitrogen. The chromatogram shown of a VOC mixture here, with in detail the separation of the very volatiles, shows the opportunities we get applying these microtraps in combination with higher cold trap temperatures, in this case -10 degrees. In fact, a same peak sharpness of around 3 seconds was obtained for vinyl chloride. From the previous research experiment, the idea came to apply a plot column, both as trapping capillary and analytical column, used to separate some very volatile compounds. Exactly the same methodology as shown in the previous slides can be applied here, and here using only -40 degrees delivered by a cryostat device. We could trap and separate nicely some very volatile compounds such as propene, methanethiol and dimethyl sulfide. Let's move on to what on-column refocusing can contribute to a dynamic headspace enrichment approach for the analysis of very volatile and volatile compounds. The dynamic headspace technique involves a continuous purging of the headspace of the sample, increasing this way the sensitivity obtained, compared to static headspace, but maintaining the low selectivity and so the high ability to do more complete VOC profiling. Again, we focus on the analysis of water samples and for very volatile and more difficult hydrophilic compounds. The volatiles are trapped first onto an adsorbent tube kept at around room temperature during dynamic enrichment. Afterwards, this first high-capacity adsorbent trap is thermally desorbed and compounds are refocused into a PTV injector before they are injected towards the column by heating up this injector. From left to right, this slide summarizes all steps performed during a classical dynamic headspace enrichment. A double needle lets in the carrier gas into the sample vial. The headspace is purged and compounds are enriched onto the high-capacity trap. Optionally, a dry purge step is performed using an empty cavity or vial to perform water management of the trap. Then thermal desorption is performed. Compounds are trapped in the PTV injector before they are transferred to the column by rapidly heating up the injector. An MPS robotic system mounted on a GCMS equipped with the DHS hardware is shown now. When we want to do trace level VOC analysis with DHS, splitless injection is a must. The highly inert thermal desorption PTV combination without the use of valves, tubing or shortly, without any existing transfer lines or interfaces, ensures complete transfer of the target volatiles. Even more, based on its forward flushed trapping principle in the injector, equipped with a very narrow, normally also Tenax filled liner, the trapping here is non-selective, so universal, meaning that complete unknown VOC screening is perfectly possible. Again, even so, in case of dynamic headspace sampling followed by thermal desorption and PTV injection, the transfer of the very volatile compounds towards the analytical column can be too slow, again resulting in contribution to band broadening and peak distortion. By implementing here the on-column refocusing and programming the CTS to be cold when the PTV is heating up and injecting, we are able to do a perfect splitless injection of the very volatile compounds. This results in a complete and very sensitive analysis of the typical VOC compounds, where the very volatiles are refocused perfectly, resulting in very sharp peaks, and an overall impressive sensitivity for all volatile compounds when sufficiently present in the headspace. Nanogram per liter down to picogram per liter concentration levels can be reached. One set of DHS TDU PTV parameters deliver a total VOC profile using a carbon-based high-capacity adsorbent trap. A cryostat cooling temperature of -40 degrees is sufficient to trap the volatiles, considering a correctly made on-column capillary trapping setup. A summary of all parameters is given in this slide that will eventually be combined in a DHS acquisition method. Some important parameters are highlighted here, as these will determine if all type of compounds can be analyzed. These specific parameters, incubation enrichment temperature, purge volume and flow, and the necessary dry purge step, can be optimized also for some typical VOC applications or for difficult to enrich hydrophilic compounds. A currently hot application that can clarify more the previous slide is the analysis of epichlorohydrin in water, for years analyzed by purge and trap as the standard technique to be used, but suffering with low robustness in routine and no flexibility towards general screening of a wide range of volatiles, especially also the hydrophilic compounds and other volatiles with very diverse chemical properties. In fact, when applying DHS with refocusing here, DHS parameters were needed to be optimized, this to enhance the presence of epichlorohydrin in the headspace, and to sufficiently enrich this compound from the headspace. On column, refocusing improved at the same time the sharpness of the peak of this compound, difficult to analyze in GC. A detection limit of 2.5 ppt is reached, while the new norm in Europe requires 30 ppt as LOQ. Important to mention is the correct choice of selected ions to be measured in order to qualify and quantify epichlorohydrin. The mass spectrum doesn't contain many ions, and moreover most of them with low selectivity. Ions 62, 64 and 49, not at all the most abundant, need to be used here. Ion with mass 57, most abundant, however, useless as selective ion when determining epichlorohydrin, even in clean water, due to the many spectral interferences that can occur. Epichlorohydrin could be analyzed well in the range of 25 to 1000 ppt using deuterated benzene as internal standard. High precision, also at low level, was obtained. DHS can be used in different modes. Where the topic of today, and the time doesn't allow us to go too much in detail in the huge flexibility of the technique, I only highlight what we discussed already and also the possibility to use DHS in the multivolatile mode, MVM, which gives us the opportunity to combine multiple DHS enrichment steps in one single analysis of one single sample. MVM is illustrated here, where for example 3 different DHS enrichment methods on the same sample are applied, using possibly different high capacity adsorbent traps and of course also a different set of DHS enrichment parameters. Afterwards, the 3 tubes are subsequently thermally desorbed in the TDU and volatile compounds are trapped all together in the PTV. When the PTV is heated, all is transferred to the column, resulting in one single chromatogram for this specific sample. Besides full evaporation DHS, MVM delivers the best way to reach a complete profile of the volatile compounds present in the sample. And therefore, MVM was taken into consideration here, as we now are able to combine a DHS enrichment step for general VOC screening for compounds easily analyzed by a headspace technique with an additional DHS step implementing the typical parameters, for instance used for epichlorohydrin. Suddenly, we finalize with a more complete VOC screening method covering a wide range of different VOC compounds. Refocusing was applied to improve headspace analysis in general and to increase the analytical performance of our traditional headspace techniques. But please also look further to what opportunities we get regarding type of sample, market to be reached, and the use in combination with all headspace techniques we have in our portfolio. This small schematic drawing positions each headspace technique in terms of sensitivity, but also in terms of selectivity, where low selectivity equals a more universal technique for the screening of volatiles. As everything becomes quite complex, it could be a handy tool to rapidly determine the best applicable technique to be used for your application. Still, not only a simple schematic drawing can immediately deliver the right answer to our analytical problem. Sometimes several techniques need to be explored, and here you can find an example where headspace SPME in combination with on-column refocusing finally turned out to be the best solution. This in terms of sensitivity, nature of the compound, a difficult amine compound, and the matrix to be analyzed, which was a DMSO extract. This very volatile compound eluting around 5 minutes, often showing a bad peak shape, could perfectly be refocused and with sufficient sensitivity enriched from the matrix, without too much interference from the matrix. We discussed some improvements done in headspace sample introduction. Let's move on to liquid injection, and more specific large volume injection, LVI, which recently gained a lot in robustness and which is often still not correctly used and therefore easily ignored in routine analysis. Large volume injection is normally done by injecting a high amount of sample, generally in the range of 25 microliters to 100 microliter, into an empty capillary, which is vented, or directly into a cold PTV injector where the solvent is evaporated inside the liner, concentrating the target compounds in the liner and afterwards heated to transfer these target compounds in splitless mode towards the analytical column. We come back to our good GC injection, which is an injection without alteration of the sample injected, so also without any discrimination. The formula here describes the solvent elimination speed and thus the injection speed we can handle in order to get a sufficient venting of our solvent. Several calculators assist in calculating the allowed injection speed of our liquid sample amount. Based on the type of solvent, evaporation temperature and the pressures applied, a certain injection speed is proposed, resulting in a certain vent time depending on the volume injected. This is a start in optimizing an LVI injection method. Large volume injection can be done using an early vapor exit principle where we inject on column in a pre-column and where the solvent is vented out when a valve placed at the end of the pre-column is opened, illustrated in the picture with the flow path in red. After venting and shown by the green flow path, illustrated on the right, this valve is closed and the normal GC oven temperature program launched. The little remaining solvent and the target compounds concentrated in the pre-column are transferred towards the analytical column where separation is performed. This is called a Coulomb-Column early vapor exit injection, which was recently again commercialized and introduced as a robust large volume injection technique and implemented in the well-known Mojmoa application. Another typical application for this type of LVI injection by Coulomb-Column early vapor exit is the determination of the mineral oil index in water following the ISO 93772 norm. Here, the Coulomb-Column early vapor exit enables us to inject a high amount of sample extract in hexane in order to achieve the low limit of 100 ppb in water and at the same time avoiding discrimination, as by injecting this way, the mineral oil content between C10 and C40 is completely transferred to the analytical column. Most LVI applications use quite volatile solvents where the venting temperature stays quite low, below or equal to 50 degrees, which gives us the possibility to vent off the solvent without losing the most volatile compounds in our application. In this chromatogram, where C10 to C40 hydrocarbons are separated, however, heptane was selected as a solvent to be injected, and therefore a higher vent-off temperature in the oven of 80 degrees was needed to sufficiently evaporate the solvent. Remarkably, still no discrimination was observed for C10, which proves the Coulomb-Column early vapor exit system to be a powerful tool for large volume injection. The PTV, as shown in this slide, has already long time been a robust standard for LVI injection. However, encountering difficulties with the discrimination of the most volatile compounds, especially when running the Mojmoa or mineral oil index application. Here, quantification is based on the integrated hump in the chromatogram, analyzed by FID, and no discrimination is allowed. As venting of the solvent is done in the narrow PTV liner with small internal volume, it is clear that venting parameters need to be optimized carefully. However, even with a glass beads filled liner for better solvent contact and more performant venting, it was difficult to obtain a similar chromatogram as with the Coulomb-Column early vapor exit setup. In order to avoid discrimination of the most volatile hydrocarbons, still too much solvent was brought onto the analytical column, resulting in distorted peaks and general bad chromatography. This shown by the chromatogram in red. On the right side, an overlay is made of a typical experiment where high amount of appeller solvent is brought onto the column with and without the use of a retention gap. Therefore, when adding this retention gap to our LVI experiment using the PTV, the chromatography came back. So a compromise has to be made regarding venting of the solvent, and an additional tool was applied to solve the issue with the amount of solvent left in the PTV liner. Discrimination of the volatile hydrocarbons using a 100 microliter LVI injection of hexane was avoided. Possible co-eluting and fast eluting impurities increase the area of the C10 peak. Still, of course, a quite large solvent peak stays present when optimizing this LVI PTV injection. The same analysis was performed also with heptane as solvent at 80 degrees for a hydrocarbon mixture as well as for a real mineral oil extract. Here, a little discrimination was observed for the most volatile hydrocarbons as expected using the LVI-PTV combination. Hereby, I'm at the end of my presentation. I still want to thank everyone from the IRC Technologies team and of course you all for your attention.